Hey, good afternoon, everybody. I'm down here in the right-hand corner just because I couldn't get the full screen thing to work with my slides. Who knows why? Um, there's a problem or an interesting question that came up. Um, I was associated with another class a while back, and some students were having a discussion about special effects in movies and taking advantage or misrepresenting some actual physics in movies. And that's one of the things that I don't like about some science fiction anymore. So we had a discussion about, particularly, this was a few years ago, we had a discussion about John Carter on Mars, which was, from what I understand, I've never seen it, but I understand it wasn't all that great a movie. But one of the things I think they got very, very wrong was some of the physics of how high someone of moderate athletic ability could jump on Mars. So I thought we'd just kind of look at it for a minute. I found out the real answer of what we really can do, and I knew that was true, but because I'm kind of skeptical, I thought I'd go ahead and check for it myself. Just a minute to make this thing work. Here we go. You may have some issues with my picture being on here. I hope not, but it seems to be. I know what I'll do. I think I can move it. Yeah, maybe. Okay. That's more or less out of the way. Problems like this are usually referred to as projectile or free fall problems. What we mean by that is once you start moving, either launching a projectile, jumping up in the air yourself, or anything like that, once you have propelled yourself where you want to go, you're only under the force of gravity. That's the only thing that is allowing you to stay in the air or trying to pull you down. That's called free fall or jumping, or that's when we kind of assume things are like weightless. But also need to talk about energy conversion here because when we jump up in the air, we start off with a pretty high velocity. When we get to the highest point we get in the air, we've run out of velocity, which means we've run out of energy. Well, first of all, I want to see how high someone could jump on the Earth. And I looked it up on Google or someplace, I forgot where now. But I found out that a person named Javier Sotomayor from Cuba in 1993 set what I believe to be still the current world record for high jumping, which is almost 2.5 meters. I was impressed. And that's on the Earth, probably somewhere around the equator. But this was fictional, what I was talking about. And I wanted to keep the numbers kind of simple. So I said, well, let's say that John Carter on the Earth can jump 1 meter in the air. And my assertion or my reason for doing that is because I wanted to keep my math a little bit simple, and we'll see if that works out okay. So what I want to do is I want to compare how high this fictional person or anybody could jump on the Earth, or let me rephrase what I just said, how if someone could jump 1 meter on the Earth, how high could they jump on Mars? We'll just see how that works out. So let's see first what velocity one has to achieve to get in the air 1 meter. We look at that kind of fully. We want to use conservation of energy, and we start off with the sum of kinetic energy and potential energy. Those are going to equal a constant, the total energy available, because what happens, you're going to jump up, whoever tries this is going to jump up with an initial velocity. As soon as you jump up, gravity is going to begin to act on you, and if gravity begins to act on you, your velocity will decrease. Once you get to your highest point, your energy is all gone, and you're going to begin to fall back to Earth. So when we start off, like I just said, there is no potential energy. When you're starting to jump, starting the process, you're just jumping up, you have a real high velocity, kind of high velocity, and you jump up. When you get to the highest point, you've run out of velocity and you've run out of energy. It's all been converted back and stored in that little split second where you're not moving at all. I'm sure there is one. And then as you begin to fall back to Earth, that energy is then released to allow you to go back to Earth. So in the beginning, John Carter jumps in the air, He negatively accelerates or slows down until he gets to zero at the highest point where his velocity becomes to zero. So what we want to find out in this part of the problem is what his velocity must be to get to the highest point. Well, like I said up here in this part of the equation, we start off with the kinetic energy that John Carter has and the potential energy that he has. Initially, it's zero potential energy because he's jumping up. It's all potential. It's all velocity trying to get high in the air. We're looking for that V right there. Then when we get up to the highest point that he gets to, this means that the energy that was spent to get to that point now equals the gravitational potential energy. In English, that's just the amount of energy one starts with is the amount of energy one ends with. It's just now been converted, at least for a moment, it's been converted to potential energy. Well, how do we know what conditions will be met when you jump in the air? Well, Newton's law of gravity can tell us what's the acceleration due to gravity, or how much we say at conversation, we say, what's the force of gravity on us? It's really acceleration. The force depends on our weight, which depends on our mass. The force of gravity is equal to the universal gravitational constant, the product of that, and the mass of the planet we're on, and the mass of us, or the projectile, divided by the radius of the planet we're on, or the separation distance between the two masses. So, high jumping on the Earth. How much does the gravity affect us? Well, let's just see. So our force between the Earth and the projectile, us, and I've highlighted that in yellow, and that's about 76 kilograms, which is, I think, if I remember correctly, that corresponds to an average-sized man. Your weight in newtons, because I'm being all metric here, because I'm progressive, at least in physics, is in newtons, which is the metric, the SI unit for weight or for force. But what we really want to find here is the acceleration due to gravity on the Earth, which will cause our weight. So that just equals here, the weight equals the product of mass times the acceleration due to gravity, right there. The acceleration due to gravity is just equal to the mass that I was just talking about, this m2 here, times that acceleration due to gravity. And what I can call that, I can say, well, that 732 that I was just talking about, divide that by 76.2, and I'll get 9.6, which I'm saying it's pretty close. The acceleration of gravity on the equator at sea level is about 9.8. It's a little rounding error there, I don't know. But I can call that 10 anyway, 10 meters per square second. That's the acceleration of gravity, and that makes the numbers really easy, I hope. So from this earlier chart we talked about, what we need to have happen when we get to the highest point we want to get to is we need to have we need to know what the highest point is. So we're solving here for the height, h. Notice I've crossed out the n's here. Even though I discussed them up here, I didn't really need to. I just wanted to put that in just for conversation, because the velocity that we need is independent of mass when discussed in gravity. So we have this 1/2 v squared equals gh, which is acceleration due to gravity that we just figured out, which is about 10. And we know we're trying to get 1 meter in the air, so that's just 1. So when we solve for v squared, we just kind of change this around a little bit. Then we take the square root, and we get the velocity that we need is 4.5 meters per second. That's all it is to it. Now that's the velocity that John Carter would need to jump 1 meter in the air on the Earth. All right. After John Carter's done that, he still wants to go to Mars and jump through exactly the same thing on Mars. Mars is a little bit different, or a lot different. John Carter has the same mass because mass is the same everywhere. But the mass of Mars is different. It's a smaller planet, and it's less massive. It's also has a smaller radius. So John's weight in newtons is about 38 to 40% of what it is on the Earth, which means his acceleration when he jumps up in the air is about 38%, which means that's less resistance to him moving up in the air. Therefore, he can go higher. So according to this calculation, John Carter can get about 2.6 meters in the air on the Earth, which is cool. About 3 meters, almost 3 meters up. That's pretty cool, but that's not 300 meters cool. That's the movie was forecasting, so it's not as great as it could be. All right, so somebody figured this out before me. Actually, lots of folks have. If you're on YouTube, you can go Google that, but I wanted to show you the calculations. Some people just hand wave, and I've done enough of that. I don't like to. But this website, Film School Rejects, published an article about it, and they come up with almost the same number I did. But I was skeptical, so I wanted to just check it out. I do hope that you like this little presentation. My bonus question for you that I will leave it to the viewer to decide. Given what we found out here, how high could Mr. Sotomayor jump on Mars if he ever was to get there and still be able to? Hope you like this. Have a very good day.